Hi everyone, and welcome to today's lecture. We're going to talk a little bit today about dispersion, so how data varies around the mean. We're going to talk a little bit today about z-scores, so finding scores that are outliers or that could potentially skew our mean. And we're going to also talk a little bit about chi-square statistics, so that allows us to compare in a hypothesis test using categorical variables. Excuse me, I have the hiccup. So what we're going to do is we're going to get into this. I may use the SPSS data set that is the supermarket data set that should be located in the data analysis assignments data sets under supermarket data. I may play around with that. I also will have another YouTube tutorial that looks at descriptives up on YouTube as well. So you should be watching that to learn how to do some of the descriptive statistics using SPSS. So we're going to start off, and I'm going to do some bouncing back and forth between my slides, between maybe SPSS, and between myself talking. I'm going to share the screen, and hopefully this works, and we will go from there. So we're talking today about sample statistics, and we talked last time about differences in measurement levels. We recapped that. We talked about categorical variables, so the differences between nominal variables, which are name only, rank does not matter. We talked about ordinal variables, which are categorical variables that have an order, where order is important. And we talked about moving from nominal to ordinal was weakest to strongest. And then we talked about getting even stronger form of measurement. So as we moved into continuous levels of measurement, we talked about interval. And if you recall, interval has no true zero. So a scale, a typical Likert type scale, a 5-point scale, a 10-point scale, tends to be interval. And we talked about ratio scales where there is a true zero. So things that start from 0 and go to whatever, such as income. If you ask somebody to write what their income is rather than describe it as a group. Typically, we're using interval scales because it has the most form of measurement of nominal, ordinal, and interval. We said ordinal and interval kind of can go back and forth, but it depends on what type of operation we're doing. So we said that ordinal obviously is weaker form. We can only find frequency counts, but we could also go a little bit stronger and use interval scales as well to give us more data. So again, you'll have to recall this information from the last time because we're not going to dwell too much on that. We did speak a lot about central tendency. Last time we talked about the middle of the data. We talked about the mean. We talked about the median. We talked about the mode. The mean was the average of the data. The median was the upper and lower 50% of the data, so essentially the midpoint. And the mode was the most often, the data that was found the most often in our set. And what we also said was that the mean could only be used for continuous variables, whereas the mean, median, mode could be used for all the variables. And the reason we said that the mean could be used for only continuous variables was because continuous variables allow us to do our full set of arithmetic operations. So the only way you can calculate a mean is if you have a continuous variable. We said also that means were likely to be skewed by outliers, so points of data that were far from the distribution of the normal distribution. And as a result, they could skew the mean. So if you recall, we used salary, for instance, and we said that the $250,000 salary vastly skewed the rest of the 6 salaries we had in our data set. So we would use the median when we notice that we have a heavily skewed distribution. Or whether we have a distribution that has a couple of outliers, or we can look to remove outliers. So we'll talk about that today. So that was, again, a recap of what we had already done, and so you recall that. You have the slides for that as well. Today we're going to talk about descriptive statistics more. We're going to finish that off. We'll talk a little bit about dispersion. So dispersion is the concept that describes data around the mean. We'll talk a little bit more about z-scores. So what z-scores allow us to do is find data points for a variable that are way outside the standard deviations, so way outside the normal distribution. And we'll also talk a little bit about chi-square, again, which is a test statistic we use to test differences and associations between categorical variables. So that's essentially what we're going to be talking about today. Again, I'll bring a little bit of a recap back for you. Do that now. Okay. Again, levels of variables measurement. Categorical, continuous. Categorical has nominal and ordinal. Continuous has interval and ratio. In SPSS, we can choose between nominal, ordinal, or continuous variables. And SPSS calls continuous variables scale variables. And again, we said this matters because it determines what type of analysis we can do with the data we have. Again, we can only do frequencies with categorical variables. We can do anything with continuous variables. So categorical variables can only use median and mode, whereas continuous variables can use mean and median and mode. And obviously, because we get more information when we use continuous variables, the mean is a more descriptive statistic than median and mode when we have continuous variables. Why? Because if you recall, continuous variables are the highest form and strongest form of measurement level. And we see that here on this chart as well, which you've seen in previous slides. Okay? So last time we talked about summarizing univariate data, and you recall this, that we started our little tree here on descriptive statistics. So we're talking about mean, we're talking about standard deviation, we're talking about variance. We talked about mean, median, and mode. Here is a normal distribution, so it's symmetric. The mode is the most frequent number, the median is the middle number, and the mean is the average. In a symmetric distribution, that's fairly obvious, right? However, in an asymmetric distribution where there's some sort of skew, where numbers in this instance are very much skewed towards the left, then the mode, again, is the most frequent number, so you see that the highest. The median splits the data 50%, so you can see a lot of data on this half, and then here it tapers down, so there's not as much data here. And then the mean, again, is the average, which looks in this instance to be around the middle of the distribution, but obviously it's skewed. So there's a lot, we said, that's going on here. So again, just remembering the basic statistics. Okay? So what the mean is, what the median is, what the mode is. Alright, so we're going to start talking, because now we've talked about central tendency. We've talked about what it is that is around the middle of the data. We're going to move on towards dispersion. Okay, so we can talk about quartiles, we can talk about shape. We did talk a little bit about shape in that chart. We're going to talk about dispersion. There are a couple of different measures of dispersion. The range, the interquartile range, these are essentially the minimum, the maximum minus the minimum, so how far the data is. We're not going to spend too much time on the coefficient of variation. In fact, they're in the appendix slides. What I want to get into today is talking about variance and standard deviation. And you've taken statistics before. So you may recall standard deviation and variance. And in a normal class setting, I would ask who might remember what these terms mean, but we're kind of not in a standard class setting right now, so we'll keep going, and I'll kind of talk about them a little bit more if you don't remember, because that's obviously what we're getting into. So dispersion itself talks about the spread or the variation, the variability of data values from our sample set. Okay? What we want to know is, how does our sample show variation? Because when we get into hypothesis testing, we want to show that this variation in one statistic versus the other statistic is an actual phenomenon rather than random. Because random would show variation all over the place. But in a normal distribution, we would find that in a phenomenon that data centered around the mean, and it varies in a specific pattern. So you can see here, for instance, that this is the same center, the same mean, but that these two curves, this one and this one, have drastically different variations, right? This one's variance is relatively narrow, and this one's variation is relatively wider, okay? Same mean, different variation. Okay, so what is variance? Well, we again talked about the difference between sample and population. So there's sample variance and there's population variance. And we can test for the sample variance because we will have a sample of data. It will be more difficult to test for the population variance. So on this slide, you'll notice that I say that the variances, the sample variance in particular, is the average approximately of squared deviations of values from the mean. So what the heck does that mean? We are looking for how far a data point is from the average. So let's say you're filling out a response and you're filling out what your preferred mode of communication is. Let's just prefer communication. How much on a scale of 1 to 5 do you prefer to be communicated by email? You know, if you're a consumer and you want to do, or you're a marketer and you want to do mass marketing and you want to do an email blitz, you want to find out how your consumers respond to email, okay? So we give that question on a 1 to 5 scale to a bunch of people. Let's go back to me for a second. Okay. So we have on a scale of 1 to 5 how much you prefer email, okay? And we get 100 people to show us what their preference is. And let's say the mean is 50. Okay, just for hypotheticals, okay? Let's say that my response, well, if we're doing a scale of 1 to 5, it would actually be a 3, okay? Right, because 3 is the midpoint. Okay, so let's say my response is a 5. Well, how far am I from the mean? Well, we want to find out what the variation is between my particular response and the mean. And we want to find out what this person's response is and how far it is from the mean, and that person's response and how far that person is from the mean, because ultimately what we're finding is the difference between each 100 persons individual response from the mean of 3. Okay, the mean could be 3.62, right, depending on our data, depending on our sampling. How far is my 5 response from 3.62? How far is that person's 2 response from 3.62? How far is that person's one response from 3.62? So what we're doing is we're finding the difference from all these people's response to the mean, and then we're averaging that. Okay? We're squaring it because we can't have negative numbers. That's a whole nother subject we're not going to get into too much on. But again, I want to get less into the how these statistics happen, because you've already done that, and get into what we're actually trying to achieve with them. And so this is kind of a building block lesson that we're talking about today when we talk about standard deviation and variance. Again, because you've already had the basic statistics, we want to get into what actually we do with them. So let me go back to the PowerPoint. And I said we have a mean, a sample size, so a sample variance. So we have the ith value of the variable x. What does that mean? Well, that means what my score response say. So I said 5. I'm subtracting out the mean, which was 3.62. I'm squaring that. Then I'm going to add that to the next person, okay? Their response was a 2. I'm subtracting out the sample size, which was the mean. So that was a 3.62, and I'm squaring that again because we can't have negative numbers. I'm subtracting out this person's 4. I'm subtracting 4 minus 3.62 squared, and so forth. And then because this is a sample, I'm dividing all of that by the sample size minus 1. So in this instance, it would be 100 minus 1, which is equal to 99. Okay? What we're going to do in this class is you're not going to be calculating, like you did in a statistics class previously, all of the squared deviations of values from the mean and then subtracting n minus 1 to do an average, right? We're not going to do that in this class, because we're going to start working with more data than you previously done in statistics, which were building blocks. We're going to be working with SPSS to calculate what the variance is, okay? So you don't have to worry about that at this point. Now, you may need to know what the variance calculation is, but in terms of calculating variance, we're not going to be dealing with that. Okay, because if you have 150, you're not going to subtract 0.1 from the mean, square it, 0.2 from the means, the mean from 0.2 and square it, the mean from 0.3 square it, plus the mean from 0.4 and square it, and then you're not going to do that. Okay, we're now past the point. Think of this like when you're in school, high school or middle school or elementary school, and they start to say, okay, you now know the arithmetic, and you don't need to use calculate it all by hand. You get to use the calculator. Okay, we're at the point where we're starting to we know the building blocks, but now we're going to start to use our stats package to do the calculations stuff. Okay, all right, so we talked about the variance, and we said again that there's a difference between the sample, which we know because we have a sample, and the population, which we don't know, and we don't have all of the population. So you'll notice here, first of all, that I start using the Greek letters sigma squared, because we're talking about the population. So you would use that to test a hypothesis. And again, with a mu, when we're talking about the population mean instead of x bar. So you'll notice that square off the bat, that's one thing that's different. That's pretty much the basic. Then the other thing you'll notice is because we don't know the population, we have the big N here to determine the population size. We don't have a sample, we have the population. So again, and you'll notice even in my definition, I'll go back, the sample variance was the approximate average because we used n minus 1. Now we're just going to use n to show the actual population variance. Again, when we talk about population variance, we're really talking more in terms of hypothesis testing because we don't have the population. So we're hypothesizing about the population. So you'll notice again, like I said, I'll reiterate the Greek letters there. Okay? But when we're running our calculations, we're really doing this because we don't this is what we have. We have a sample, okay? So sample variance, population variance, okay? So let me go back here. Again, you'll notice that these are squared, right? You'll notice that this is population variance is sigma squared. This was S squared, right? This is the average of squared deviations of values from around the mean. Okay, that's great. We have all this information. This is a ton of information that we have when we use variance. But what we typically use when we talk about dispersion is we talk about standard deviation. And what this is showing the general variation of data around the mean. So we're not just talking about the average squared deviations around the mean. We're now actually talking about the average deviations around the mean. Okay? So what is the standard deviation? This is the square root of the variance. So you'll notice, for instance, this was the sample variance formula, right? Now we square root it, and now we're back to the standard deviation. It is in the same units as the original data. So think about our phone example in one of our early lectures where we said we hypothesized the average cell phone bill in the city was $42, okay? So that was the mean. What is the standard deviation if it is 7? A standard deviation of 7. Because I thought about this, and it took me a while. I took it in my master's class, was really trying to figure out what the heck standard deviation meant in plain English. Well, in plain English, standard deviation is kind of the plus or minus, right? You know, when you see a poll, you get a statistic. Let me bounce back for a second so I can see you guys. Okay, remember when you have a statistic like in a poll data where it says the standard of error, the standard, you know, plus or minus 3%, right? That's a standard deviation. And what it actually is saying is that one standard deviation, or about 68% of the sample, is between plus this from the mean and minus this from the mean. So let's say it was plus, you know, a standard deviation of $42 was the mean, the average we hypothesized, and the standard deviation was 7. Okay, so what we're really talking about is $42 plus $7 or $42 minus $7. Okay, so we're talking about $42 plus $7 is $49, or $42 minus $7. 42 minus 7 is 35. One standard deviation, and we'll get into this in a second, is equal to about 68% of the population. So what we're saying when we talk about a standard deviation of 7 on top of a mean of $42 is that 68% of our sample falls between $35 and $49. Okay? Hopefully this makes a little bit of sense. Because as you'll see, we'll be using standard deviation quite a bit because we want to find out what standard deviation is. Okay? Alright, let me go back to my screen. Whoops, actually forgot to do that. Okay, screen share. Alright, so here's was the standard deviation. And again, just like I said, standard deviation was $7, right? Because we have it as the same units as the original data. So I had said that it was $42 plus or minus a standard deviation of 7. 7 is in dollars, okay? And again, we said the same thing. We're doing a sample versus a population. We have a statistic for the population. It is the same as the variance. You can see it's just n. It uses mu. It uses sigma. Pretty much the difference. Again, the reason is because we have a sample. We don't have the population. Okay? So I mentioned 68%. Where do I get that from? Well, I get that from this distribution of variance, okay? We have a mean that's in the middle of a normal distribution. You guys probably remember bell curves, right? Gaussian distribution, normal distribution. You know, that the data in a population, especially a random population, a randomly selected population, the data normally distributes normally, right, around this bell curve. So when we talk about a distribution in terms of standard deviation, what we're talking about is -1 standard deviation, which is 34.1% of the population, or +1 standard deviation, which is 34.1% of the population. So we have a plus and we have a minus standard deviation, right? People who are above the mean, people who are below the mean. Remember, I said 3.62 was the mean for our email preference, and I said mine was 5. That was above the mean, right? So I would be in the plus standard deviation, as opposed to the minus standard deviation, or below the mean, okay? So in a normal population, data distributes around the mean, the central tendency, and the bulk of the people in a normal bell curve distribution are around the middle. And then we start to move outside the middle, where fewer people have these responses, fewer people are these things. And then we move out even farther towards 2, 3 standard deviations, okay? So the distribution of variation around one distribution is about 68.2%. Plus, if we get out, we're adding 13.6 here on this side and 13.6 on this side. We're talking about almost 95% of the population. And we move towards 3 standard deviations, we're now talking at about 99.7% of the population, okay? So 3 standard deviations is about 99.7% of the population. So again, looking here at a different way of, you know, the normal shaped bell curve, okay? Again, 1 standard deviation, 2 standard deviations, 3 standard deviations, and then this even goes out to 4 standard deviations. By the time you get out past 3 standard deviations, and you're talking about 99.7% of the population, you're talking about the bulk of observations. So generally, we're looking at maximum of -3 to +3 standard deviations in our samples, okay? And you can see here on this chart that it aligns with cumulative percentages. So 0.1%, 2.3%. Here's 50%. What's another term for 50% if that's the mean? The median, right? So on a normal bell-shaped curve, the mean is also equal to the median. Okay? You can see here we keep going. Plus 50 plus 34.13 is 84.1. Plus another 13.59 is 97.7%. So we'll keep on moving out towards. And again, here's a percentile-based version of it, okay? So we now have a sense of how data distributes in a normal distribution, a bell-shaped distribution. Okay. This is important, again, to reiterate because of the empirical rule. And this empirical rule is kind of essentially what I just said, right? If the data distribution is approximately bell-shaped, then the interval of the average, or mu, the mean, plus or minus 1 standard deviation contains about 68% of the values in the population. So when we talked about the cell phone bill as $42, and we said that the standard deviation was 7 or $7 because it's the same units, then what we're really saying is that that is plus or minus standard deviation of 7 contains about 68% of the values of the population. So again, I said this before, but it comes back now, what we've already said with this empirical rule. 68% of the values are between 35 and 49 because the mean was 42 plus 1 standard deviation was plus 7 is 49 minus 1 standard deviation, so 42 minus 7 is 35. So that was the range of the 68%, okay? Plus 2 standard deviations. So now we would have to calculate what 2 standard deviations is, okay? That contains about 95% of the population or sample. Plus or minus 3 standard deviations contains about 99.7%, okay? So again, we said that it was really dependent on how far out we want to go. If we want to find out if you're beyond, 3 standard deviations, you're essentially beyond 99.7% of the observations that we have, okay? You're in 0.3%, okay? Where does this curve look familiar? Taken principles of marketing class, you look at the diffusion of innovation curve, the Rogers innovation adoption curve, okay? Many of you may remember this, okay, right? Innovativeness is a time at which individual adopts. Continuous, it's partitioned into 5 adopter categories by laying off standard deviations from the average time of adoption, okay? So in this instance, the mean, X bar, is the average time of adoption. And this curve is based on standard deviations from the average time of adoption. So standard deviation is right there, okay? This is not just a random concept that we are using, to have a bunch of numbers. This is a concept that we use in applied marketing. So this standard deviation, the early majority, just back on the empirical rule, 34%, rounded. Late majority, 34%. The majority of people are in that empirical rule, plus or minus 1 standard deviation, or 68%, okay? The early adopters were the second standard, minus 2 standard deviations, or 13.5%, okay? We have innovators who were another 2.5%, okay? And based on their theory, they said the laggards were totally 16%. Maybe they wanted to not split this up. But you see, again, that this follows the empirical rule, right? It's right by the mean and how many people adopt it around the mean, okay? And we can compare standard deviations with our data. For instance, we have the same mean here. We have a mean of 15.5. So let's say that's 15.5 is equal to $15.50, okay? That's the same thing. I just added the 0 so we can make this into practical terms, right? $15.50. This has a standard deviation of $3.34, okay? Same mean. $15.50 with a standard deviation of 93 cents, okay? You see that the mean is much more distributed around the center than in data A. In data C, we have a mean of $15.50 with a standard deviation of $4.57, okay? And you see here that the data is way on the outsides here. So we have the same mean in data A, B, and C, but our standard deviation changes, and as a result, you see a different distribution in each, okay? So that helps us to draw some comparisons between different groups, what our mean is and what our standard deviation. So here we saw this chart in the very beginning or towards the beginning of our lecture. We saw that this was the same mean but with a large standard deviation and with a small standard deviation. So this might be the standard deviation here, very close to the mean, versus a very wide standard deviation here in a large, okay? What are the advantages of variance and standard deviation? And this is important because we've talked about measurement levels, and we're going to use this when we start getting into some of the hypothesis testing. Again, I mentioned that these are building block lectures, and I'm trying to apply them. And ultimately, when we get into the hypothesis testing, that's when the real application is going to come in. Because right now, we can use this to describe our samples, right? We said these are descriptive statistics. I can say descriptively that the average cell phone bill in Boston was $42 plus or minus a standard deviation of 7, right? That's a description of my sample. But that doesn't test anything, okay? But if I know what the mean is, and I know what the standard deviation is, I can start doing tests. So again, this is building blocks. So why do we use the average, the variance and the standard deviation? Okay, a couple of reasons. First of all, because each value in the data set is used in the calculation. So if you recall, I go back, and I think I just went, oh my, that's okay. If I go back, and let me go find the slide, right, to my variance and my standard deviation, you'll notice that each data point was used in the calculation, right? We said that the ith variable is used, or rather in a sample, we said that the ith variable x, right? The one data point, my 5 versus 3.2, right? We said that that would be used. So let me go back to my thing. So, oops. Okay, so if each value in the data set is used in the calculation, then that gives us a pretty good idea of what's actually going on with the distribution. What it also means is that values farther from the mean are given extra weight, because if you look at the formula itself, the deviations from the mean are squared. So that means that they show a farther distribution. But the basic gist of it is that it tells us how the data distributes or disperses or varies around the mean or the average, because we can't do much with the mean by itself. How do I tell whether two means are similar or two means are different? If I go back to this, I can have a mean of 15.5, 15.5, 15.5. That's fine. But the only thing that's going to tell me whether those two means are the same or different, just by looking at the population, is by the standard deviation. So looking at standard deviation, looking at variance, because variance explains is the ultimate, is a building block to standard deviation. That's the only way we're going to be able to determine whether or not there are differences. Okay. So let's take for a minute this concept that I wanted to just talk about briefly called the central limit theorem. And what the central limit theorem is, and there's a lot of words on this slide, is the mean of a sufficiently large number of independently variables tends to be normally distributed. We don't know the population mean, but if we pull out enough samples to fit on a normal curve, the distribution of an average would tend to be normal as the sample size increases, regardless of the distribution from which the average is taking. Okay, what does that mean? Well, look at this picture, okay? Take a sample like rolling a die, okay? I can roll a die. I have a distribution that looks like this, okay? I can get a 1, I can get a 2, a 3, a 4, a 5, and a 6, right? Each one has equal probability. As I start to add in another die, you would think that it would be 1, 2, 3, 4, 5, 6, but now I have changed my distribution, okay? But it's a normal distribution because my probabilities of 1 through 6 are equal for each die. As I do 3 dice, I get this. 5 dice, I get this. 10 dice, I get this, right? So the more I sample, the more die I add in, the more my distribution starts to approach normality, okay? And this is one thing that we get into when we talk about big data, right? You've all heard the term. Some of you are doing big data in your majors, okay? The more sample you have, the more dice you have, the more people you get, the more your data starts to approach normality. Not always, but starts to. And this is why big data likes big data, because it starts to gain a sense of what the normal distributions are. Instead of sampling, it has a large volume of samples. We call this the law of large numbers. Okay, so the central limit theorem will help them. The more data we get, the better off we can determine how our sample is supposed to be distributed in the population itself. Okay, so when we talk about descriptive measures, we've talked about central tendency, we've talked about mean, median, mode, we've talked about dispersion, so we spent a lot of time on variance and standard deviation. We have to think of a couple of things ethically, because we are reporting these for data, we are reporting these to managers and reports, we're reporting these to other people that might be using the data and not have the original data. And we need to be able to be objective, because we're essentially doing this again like a science. This is a data science. So we need to show good results. We need to show bad results. We can't cherry pick what things worked and what things didn't work, okay? Because sometimes when things don't work, we want to know why they didn't work. So just because a result is what we are hoping for or not hoping for doesn't mean that we don't report it. We need to report both good and bad results. We need to be fair and objective and neutral manner. Okay, and we don't want to use inappropriate summary measures to distort the facts. So think about when something is framed as 65% of the population doesn't like, coffee. Okay? If 65% of the population doesn't like coffee, what about the 35% that does? So presenting summary statistics is important when we want to be able to show things in a fair and objective manner. It requires some level of bias. I mean, the research, as researchers, as individuals, we're biased. But if we explain what it is we're doing, then that will help us. I mean, you think about ethical considerations in our research. Think about one of the things that's obviously very big in the news right now is whether or not data, is falsified or not falsified. And we want to be able, as scientists, to reproduce what has already happened. So in some of the harder sciences, like cloning and stem cell research, and even if you think about the discredited autism vaccine study, and we'll talk about that maybe a little bit later when we talk about correlation, one of the things is the ethics behind how we report what our findings are, how we show what we've done with our data, and being able to reproduce that reasonably by other scientists. And so we do pay ethical consideration to what our descriptives are. Okay, so just something to think about. So let's move into z-scores. Okay, now that we've talked about central tendency and dispersion, we can talk about z-scores. So what is a z-score, if you recall at all from your previous statistics class? Well, a z-score is the measure of distance from the mean. Okay, well, how's that different than standard deviation? Well, it's not. What we're actually trying to do is find out what a score is in standard deviation terms. So we'll typically call this standardizing a variable, okay? And what that allows us to do, let's go back to my example. Let's go back to the example of the cell phone bill, okay? If you have a $42 app mean and the standard deviation is $7, that's great. What happens at a standard deviation of 2? What's the cell phone bill? Well, I don't know. Why don't I know? Well, because I have to calculate what that actually is. And to do this using a z-score. So what is a z-score in formulaic terms? Well, a z-score is the difference between a value and the mean divided by the standard deviation. So we were already supposed to have calculated what our standard deviation is. We already calculated what the mean is. Now we want to know what our one score is minus the mean divided by the standard deviation, because this helps us determine whether something is or is not an outlier. And we said here a rule of thumb is that a z-score above 3.0 or below negative 3.0 is considered an outlier. Why do we choose those values? Because if we go back to this again, 3 standard deviations covers about 99.9% of the population. No, 99.7% of the population. So that's a lot of the population that we're willing to work with. So we will typically use a threshold of plus or minus 3 standard deviations. Okay? So as an example, let's say our mean is 14 and our standard deviation is 3. What is a z-score for a value of 18.5? Well, we have the formula right here, okay? The z is the score minus the mean divided by the standard deviation. Just plug it in, right? The score, 18, our value, 18.5. Our mean, 14.0. Our standard deviation, 3.0. Do the arithmetic, 1.5, right? It's fairly straightforward. And a value of 18.5, therefore, has a z-score of 1.5. And a z-score is essentially number of standard deviations. So a value of 18.5 has a z-score of 1.5. A value of 18.5 is 1.5 standard deviations above the mean. And again, as we mentioned previously, a negative z-score or negative standard deviations would mean that a value is less than the mean. Okay? This is fairly straightforward. What this essentially allows us to do is to compare different values of data in standardized deviation terms. And in particular, when we start looking at more variables, or we're doing multiple variables at once, when we want to know how this compares to that, standardization helps us get on the same page, because instead of doing units, we are operating in differences from means, the standard deviations from means. Okay? So I could be talking about sales in dollars and time in minutes, but once I find the standard deviation, once I find the z-scores, it's all in terms of standard deviations. So it's all standard, what we call standardized. So I can compare a score easier when I do it in deviation terms. So if you remember, I said one standard deviation was about 68% of the population, right? That the probability was essentially 68% of the population that fell between -1 standard deviation and +1 standard deviation. So what we typically do once we have calculated a z-score is to use a distribution table, which has a probability which goes from 0, the z-score of 1.56 in our example here. Okay, we want to find out what the probability is of our z-score between 0 and 1.56. So we have a z-score of 1.5, and we use a z-table. So we look down this column and we go to 1.5. Okay, because what we do is we start here, and then we look at our second decimal, because we only have 2 decimals in our z-score. So 1.5, and we go, this column is 0.00, 0.01, 0.02, 3, 4, 5, 6. So that's our probability, right? 1.56. If we have a z-score of 1.56, we are talking about 44.06% of the population is between 1.50 and 1.56. Okay. If I had a z-score of 2.2, I would go, 2.24, I would go down here, I would look to 2.2, and I would go to 2.24. Okay, so if I had a z-score of 2.24, I would have 0.4895, or 48 point, where's my cursor? There we go. 48.75% of the population is between 0 and, where did it go? 0.4875. 48.75 is between 0 and 2.24. Okay. Conversely, we can do the opposite if we were looking back from the other side of the population. So we would just subtract, so that would be negative. We could subtract that out if we were doing less than or equal to. So what I'd like you to do is I'd like you to think about what the probability is using the probability table. Either you can Google one or use the one on the previous slide, of finding out a z-score that is less than or equal to 1.0. Now this is important that it's less than or equal to because that's inclusive of that. When we talk about greater than or less than, we're subtracting from 1. You may recall that from your statistics class. And then we're finding out the probability. So the first question was, what is the probability of z less than or equal to 1.0? We've kind of talked about this a little bit. What is the probability of 2 greater than 2.0? Okay. And what if a new salesperson's first month performance only has a 10% chance to reach the average performance? What is the performance z-score? So essentially, you're finding out what the z-score is if they have a 10% chance of reaching the average. So think about working backwards from the probability back to the z-score. Okay? So I want you guys to think about this. Maybe we'll talk about it on class on Wednesday. We can use z-scores to identify outliers. So again, when we calculate z-scores, we can find out what they are relative to a standard deviation. And if we do that, we can do that relative to finding out plus or minus 3 standard deviations. So we can, in SPSS, calculate z-scores. We don't have to do this by hand. And we could, but we don't have to. Certainly we have a tool that makes it easy for us to do now. But you may want to know the formula anyways. So we can save the z-score into a new variable in SPSS. We can then sort the z-scores in the variables, and then we can identify cases that have z-scores higher than the decided threshold, which we said is typically plus or minus 3. And I have another SPSS tutorial that deals with z-scores, so I'm going to try and do this a little bit quickly because I don't want to spend too much time since I've already done this. If you find outliers in critical variables, consider either not including them in further analyses or conducting case studies on these unique cases. Because let's say we have that 200, remember the Suffolk salary example, if we had $250,000 salary, right? Why does that person have $250,000 salary as opposed to all of the other salaries? So we could consider looking into why that is. Before we just outright drop it. But we could also drop it as well. So there's a lot more sophisticated techniques we can use to eliminate outliers, but certainly looking at that would be important. Okay, and I have here using SPSS for z-scores, where you can actually save it as a standardized value. I'll show you really quickly here. Let me bounce back over. I'll share my SPSS screen. I had my supermarkets data, right? And one of the things I had And this is a British supermarket survey. And one of the things they ask people is, how much do you spend per month on meat? How much do you spend per month on fish? How much do you spend per month on vegetables? So let's say I wanted to find an outlier for vegetable expenditure, okay? I could go to Analyze, Descriptive Statistics, Descriptives. I choose the variable I want to use, and to find the z-scores, I can just save this standardized value as a variable. Again, because I said that z-scores are also known as standardized values. I'll click OK. It gives me my minimum, my maximum, my mean, my standard deviation. So my mean expenditure on vegetables is $10.53 with a standard deviation of 6.96 or $6.96. What does that mean again? Think about the empirical rule. $10.53 is the average. 68% of the sample of the population would be between $10.53 plus $6.96 and $10.53 minus $6.96. So we're talking about 68% of the people being between about $3.55 roughly and $17.19. Okay? All right, so that was back to that empirical rule. Okay. If I go back over here, well, you can't actually see it. It didn't actually show that other screen. Okay, that's okay. So let me just show you that here on this screen because I just want to make sure that you guys see this. Okay, $10.53 with a standard deviation of 6.96 or $6.93. Okay, I'm going to bounce back over. Okay, so here's my SPSS data again. You can see here I had the vegetable variable label. Now there's something called Z vegetable. Z, and if you hover over it, you can see that it says Z score for vegetables, okay? So this person's, or this case's vegetable expenditure was minus 0.85 standard deviations. This person's was plus 1.42 standard deviations. And again, we can use a z-score probability table and convert these back to percentages. What I can also do is I can click on the variable and right-click and say sort. Okay. Now it will sort from highest or lowest to highest, and I can then determine which ones are outliers. None of these are above 3.0. None of these are below 3.0. So there's no outliers in vegetable expenditure. Okay. Okay, let's go back. All right, so we've talked quite a bit. Let me look to make sure where I'm at about dispersion. We've talked quite a bit about z-scores. The last thing I want to get into a little bit briefly before we meet next time is about chi-square statistics, okay? Because we've done all that we really know how to do when we talk about descriptive statistics. We've talked about mean, we've talked about median, we've talked about mode. Those are all measures of central tendency. We've talked about variance, we've talked about standard deviation. Those are measures of dispersion, okay? I have some other appendix slides that are covering geometric mean, that are covering range, that are covering coefficient of variation, but we're not really going to focus on those in this class per se. Those probably won't be on the test. Maybe range might, but not coefficient of variation, not geometric mean, not. So make sure you look at them and have a sense of what they are. We might do a little bit on interquartiles. You know, the 20, it's kind of like the median, right? The 25th percent, the 50th percent, which is the median, and the 75th percentile, right? Those are quartiles, 1, 2, 0, 25, 50, 75 in our full sample. But we're not going to spend too much time because what we're really looking at is statistics that we're going to be using a little bit more in our hypothesis testing. So we've done the descriptives of our sample. We've done some categorical descriptives. We've done some continuous variable descriptives. So that way we can describe, if we get a sample, how do we describe the mean of this variable? How do we describe the median of this variable? How do we describe the mode of a variable? How do we describe the standard deviation of a variable? How do we describe the variance of a variable? The minimum and the maximum of a variable, which, you know, if you subtract one from the other and you get the range of the distribution. So he's talked about all these things that are ways to describe variables for different measurement level types. Okay, so I'm going to go back over to my slides because we're going to start talking about chi-square analysis, and that's one of our first hypothesis tests that we're going to start getting into. And I just kind of want to give you a flavor of what it is before we go. So let me redo my screen. And come on. There we go. Okay, so what you see here is that we've done on our decision tree, we've done summarizing univariate data, we've done some descriptive statistics. What we're going to move to now is the next part of our tree, where if you look at the very top level, we're exploring relationships between variables. The form of data, as you look down the tree, is frequencies, and the number of variables now is either 1, and we're comparing to a theoretical distribution. So we're comparing our sample to an estimated population mean, or 2 variables, or we're testing for association. Okay, we want to, and by testing for association, we want to see if those variables have a relationship. Okay, and whether or not a relationship between those 2 categorical variables is significant. And how do we know they're categorical variables? Because, again, go back up to the top, towards the top of the tree, we're dealing with frequency counts. Okay, so continuous data, when we're dealing with frequency counts, is going to start getting into either a one variable and we're doing a goodness of fit test, or 2 variables and we're testing for the relationship between those 2 categorical variables. So moving down. Okay, so when do we use chi-square test? We're talking about cross-tabulation tables. You may recall the last lecture we had talked about cross-tabulation tables, right? We talked about education. We could use that for frequency counts, for the mean, median, mode. We're doing ordinal variables. We do the same thing with multiple variables, such as 2 variables, where we're looking at, you know, gender by soft drink preference, right? You recall that, a row by column table. One of the things that chi-square allows us to do in practical terms is to do some market segmentation analysis, because it lets us know, 1, if one variable is similar from the sample to the population, and 2, if variables have relationships between each other. Because if we know that these categorical variables have relationships between each other, then we can start to build off market segments. You can't just say that males that are in this age group like this and know that that's an actually significant relationship, right? You have to actually test that. So we use chi-square to be able to create market segments. So we had a calculation using a cross-tabulation table. Sometimes this is known as a contingency table. Cross-tabulation is a little bit of a long term, so we typically just call it cross-tabs. Crosstabs are used to do two things. One, to test association between two or more categorical variables. And so we have the same chi-square statistic used for two different tests. One is a test for the difference between proportions. So it's the difference between the general sample versus the general population. We call this a goodness of fit test. And one is a test of independence. And we're testing to see if one categorical variable is independent from another categorical variable. We also call the chi-square test a non-parametric test. What does non-parametric mean? Well, non-parametric is a fancy word for saying we don't know if the data follows a bell curve. We don't know if the data is normally distributed. And that's tough because we can't do as many things with it, right? We're using categorical variables. We have variables that don't have all arithmetic operations available to us. So we only have frequency accounts. So how do we determine, whether or not the data is normally distributed? So we use what's called this non-parametric test to assume that the data is not normally distributed. So as a result, chi-square is a non-parametric test. Non-parametric is non-normally distributed data, okay? And we want to determine whether or not the sample is representative of the population. Again, because we can't assume that the population is normal because we only have frequency counts. So what we start to do is we start to look at whether the data that we observe in our sample behaves as we would expect it to. We call this fit, right? Does the data that's observed fit the data that we expect? Does it behave as we expect? So we use this test called chi-square difference test or the chi-square goodness of fit test. This tests for differences between two proportions, okay? We want to know whether our actual fit frequencies fit our theorized frequencies. We want to know whether our observed frequencies, our sample frequencies, fit our expected frequencies, our hypothesized frequencies. So you see here that we have observed, which are the real results, our sample results. We have the expected, which is our theorized results, our hypothesized results. And what we're doing in this test, and this is for both goodness of fit and for association, is we're comparing the frequencies between the observed frequencies and the expected frequencies. So we use this chi-square statistic. And you can see it's fairly straightforward. We have the frequencies observed, FO, minus FE, the frequencies expected. We square it, and then we divide it by the frequencies expected. And we're not going to get into all of this, but we sum it over all of the cells in our cross-tabulation table. Because you remember, a cross-tab is essentially a table. And tables are composed of cells, right? Just like in Excel, right? You have cells in Excel. This is the same thing. So we then run our hypothesis test, okay? So our hypothesis test says, for goodness of fit, the null, the boring hypothesis, this is what we otherwise would demonstrate as equal. We would want to say that the data fits a specified portion of frequencies. Okay? Or proportion, sorry, proportion. The alternative hypothesis is that the data does not fit at least one proportion of frequencies. It could be any of them. We don't know which one it is. But as long as it shows that it doesn't fit, we would reject the null hypothesis, right? So you're going to have to recall back to what we talked about with hypothesis testing. Okay, so you see here a cross-tabulation table I have of education level versus car purchases, right? And you see the frequency counts. That's our expected frequency counts. So what would our hypotheses be? What would our null be? Okay? What would the null hypothesis be? Well, think about it. Think about what I have above for the null hypothesis, and then think about our alternative hypothesis. How would we go about doing this? And I want you to think about this and think about it when we come back to class, the next class, okay? Because we then want to ask ourselves, and this is a question I'd like you to answer, why it's important for marketers to test goodness of fit data. All right. So if you recall, we had this example with phones. We had a thing where we looked at males and females versus Apples and Android phones, okay? And we had a sample here, and we had a crosstab here, right? What we then look at is what our expected frequencies are versus our observed frequencies. We can find out percentages within a particular cell. So if this was 12 and we divide it by 120, we get 10%, right? 12 out of 120, so 10% of women liked Apple, 90% of women like Android. 13.33% of males liked Apple, right? 24 divided by 180. 156 divided by 180 is 86.67, right? So you can do a lot of different just dividing, figuring out what the percentages are. SPSS will calculate this for us, but you just is getting an example of what this is. And what we call these outside the cells are the marginals. These are the margin cells, right? Okay. So 36%, so 36 frequency count out of 100 is equal to 12%. 264 is out of 100, 88%, right? These all add up 12, plus 88 is 100%, right? All this starts to add up to 100% in the marginals, okay? 40%, 60% is equal to 100%, right? This kind of makes a little bit of sense. What we start to do is we start to get the chi-square statistic. We have it. We're looking at the observed frequencies. We're looking at the expected frequencies. So what do? Well, we are given expected frequencies. We are given observed frequencies. We can run the calculation really easily. Just plug in what the observed frequency is of that cell minus the expected frequency of that cell, square it, and divide it by the expected frequency, right? And then do that for all the cells. So do it again for this cell. Do it again for this cell. Do it again for this cell, okay? Then what we do is we use something called degrees of freedom. And I'm not going to get into exactly what degrees of freedom mean, but what you would need to know for this instance is that it helps, degrees of freedom help us locate on a score table when we're testing for hypotheses. And to find the degrees of freedom for the chi-square statistic, we have multiply by the number of rows minus 1 by the number of columns minus 1. So in a 2 by 2, if we have two rows, we do 2 minus 1. Whoops. By 2 columns is 2 minus 1, so 1 times 1 is 1, okay? If we had 4 columns by 2, we would do 4 minus 1 is 3, times 2 minus 1 is 1, so that would be 3. If we had a 3 by 3 column, a table, we would do 3 minus 1 is 2, times 3 minus 1 is 2, so 2 times 2 is 4, so there would be 4 degrees of freedom, okay? So that's the formula for a chi-square degrees of freedom. Once we know what the degrees of freedom are, we can find our critical value, if you recall when we talked about hypothesis testing. In this particular instance, we look at a chi-square distribution with 1 degree of freedom, because we have 2 minus 1 is 2, times 2 minus 1 is 2. 2 minus 1 is 1, times 2 minus 1 is 1, okay? And again, if the chi-square statistic is greater than the chi-square critical value, we reject the null hypothesis. Otherwise, do not reject the null, right? Just like we've talked about in class with regards to hypothesis testing. So you see here, I've done all the math back out, okay? The frequency of observed was 12 minus 14.4. We squared that and divided by the expected frequency, 14.4, plus the next cell, plus the next cell, plus the next cell. And we now have a chi-square statistic of 0.758. Okay? Our critical value at 1 degree of freedom, if we were to go to a chi-square table, which you have as a resource listed in the course documents on Blackboard. You can Google a chi-square table as well. You see that chi-square is less than the critical value, so therefore we fail to reject the null hypothesis. We support the null hypothesis. We conclude, what was the null hypothesis? That there's no evidence that the proportions are different, right? Let me go back to that. The null hypothesis said the data fits the proportion of frequencies, so there's no difference, right? Okay, this gets a little bit confusing. So we're going to stop right there because we'll talk a little bit about the test for independence next time in the next class. But what we're kind of getting into here is this notion of, one, what chi-square is. It looks at frequencies and it determines whether our observed sample frequencies are the same frequencies that we expect them to be. And number two, what we're looking at is whether or not we can what will we get for our conclusion? Do we reject the null hypothesis or do we reject the alternate hypothesis? Again, if we reject the alternate hypothesis, we are supporting the null. If we reject the null, we're supporting the alternate. And again, our only goal for having a null, and the only reason we have a null in there, is to try and reject it. In this instance, we didn't. Okay? Again, this goes along with what we've talked about for hypothesis testing, the stuff that we've talked about in class, the video I have on hypothesis testing, which I'll put up. This all goes together, okay? So what we're going to do for next time is we're going to get, again, to finish off the chi-square test. We'll review it a little bit. We'll talk about it. And what I would like you to do for next time is to watch group videos, to critique it. I want you guys to think about what actually is going on in them, what things could have been done differently, what things could be done the same, and I also want you to think about what some of these questions I had in the slides are. For instance, what was the hypothesis in this goodness of fit test? Why is it important for marketers to test goodness of fit data? Okay. I want you to think about, answer those questions. I had a couple of other questions in some of the earlier slides as well. And then we'll also talk a little bit about the group project next time. And so let me just show you that again. I have that here. Did I have that here? I didn't have it. I don't know where my that slide went. I don't know where it went. I had a slide there. All right, well, I don't have a slide there. I thought I did. But again, oh, here we go. Here is the slide. All right, so again, we talked about dispersion, how data distributes about the mean, standard deviation, variance. We talked about z-score, so getting variables standardized in standard deviation terms so we can compare it to the rest of the population. We can also find out whether there are outliers. And we also talked about chi-square statistic. We talked about using it for two reasons. One was to determine whether or not our data fits our expected hypothesized data versus our actual sample data. using categorical variables and frequency counts, and then we're going to talk a little bit next time about, again, testing relationship between categorical. And again, we'll talk about the term project. So if anybody has any questions, I highly encourage you to use Blackboard to set up a discussion. Some of your peers might be able to answer your questions. I'll be able to answer your questions. Think about the questions that I pose in the Blackboard slides, because I really want you thinking about those to be able to bring into class on Wednesday, because I'll call people and ask for what their responses were, so that way we can go over this on Wednesday. So hopefully everybody's having a good day, and we will see you the next class. Bye-bye.